In exercise 3c, we will apply random forests. Using different values of the mtry parameter, which is the number of variables that are randomly sampled, we will grow multiple random forests for regression and classification with the data that we've discussed before. We will also illustrate a version of variable importance, the one that uses min depth, and then we will compare our results. So, first of all, here I created 6 different versions of a random forest, and they are all pretty equal regarding the parameters here, except for the mtry parameter. So the last one, R6 here, uses 30 explanatory variables or features. So this is the bagging model. And this one here is the maybe most extreme case of random forest in the cell, which only uses 5 different features of the available 30 features to train the individual trees. So I pre-run all the cells because this would take some time. But if we see the output of the models and we compare the mean of squared residuals here, we will see that actually, and those are all out of bag values, the one for the bagging model with 9.03 roughly is quite high in comparison to the other ones. And the best models are actually the one with a low value for mtry. So here the best one is the one that set mtry equal to 10 with only 8.8 as the value for the out of bag mean of squared residuals. So we see that random forest actually improves our out of bag metric quite severely, which gets even clearer when we will do it for classification. So next, we will use this min depth distribution function to get the distribution of the min depth parameter, and then we will use the distribution to plot the variable importance according to minimal depth. And we've already seen this in the lectures, so let's scroll a bit down here to the bagged model, and you see that failures here, for example, has a very low value, as we discussed before when I showed the variable importance of the bagged model. And this means that it's occurring very often at the root node, so that the average is actually approximately 0.1, so very close to 0. But now, as we introduce more and more randomness by using less and less features, we will increase this value to 2.5, which means that much less trees will actually use failure for splitting at the root node, which is obviously because they just don't have it available in the sampling, so they can't use it for splitting at the root node. And this is now the randomness that is introduced to the trees, or to the whole bagged model then, and it becomes the random forest and performs much better. So as we don't exactly know the meaning of all the variables, we won't discuss the the consequences of the importance of these features. But as you can imagine, if you do some research, this might give you a lot to talk about when you discuss the implications of your model. Also, if you compare each model with another, you will find that the most important variables won't change. So they are still pretty robust. So next we do the same thing for classification. So we train the 6 models for classification using our classification dataset, and then varying the mtry parameter. Now if we have a look at the return, we will see again our out-of-bag estimation of error rate, and then the confusion matrix. And the confusion matrix doesn't really change that much, but if we have a look again at the out-of-bag estimation and the out-of-bag, I mean the bagged model out-of-bag estimation error, then we see again that it's higher than the one, for example, of the second random forest model, which uses a mtry equals to 10, which is roughly 1% point lower, or 1.5% points lower than the bagged model, which is quite a nice increase. And now we can go even further and say, well, why won't we choose a different tree size? I have to mention again that in the lecture you discussed, now if you don't want to check out all the different possible values for your mtry parameter, that setting m roughly to the square root of the number of parameters that you have available is a good value for the mtry parameter. Now, you could also vary the tree size a little bit. For example, I tested here 4 different sizes: 1,000 trees, 1,500, 2,000, and 2,500 trees. So I just will iterate over these numbers and print the result for the different tree models. And we will see that actually here the 2,000 tree model performs best. So this is also a nice increase in performance measured by a decrease in out-of-bag estimation of the error rate.